In section 2.3, we learned how to solve second-order linear non-homogeneous ODEs with constant coefficients using variation of parameters. What we are about to do for the next week or so is we're going to learn how to solve some of the same ODEs using a different method called Laplace transforms. There are some things that variation of parameters can do that Laplace transforms can't. And there are some things that Laplace transforms do really well that variation of parameters kind of struggles with. So there's kind of a little bit of motivation to learn both methods. The Laplace transform is an operator, which means it's kind of like a derivative or an integral. It acts on a function to produce a different function. And this formula right here is the definition of Laplace transform. So it's an improper integral because it goes from 0 to infinity. And the function it acts on is this lowercase f of t function. And in the end, whenever you are done taking your Laplace transform, this is going to give you a different function. We're going to use a capital letter to represent the function after the Laplace transform. And it's no longer a function of the variable t because we integrate with respect to t, so the t variable goes away. Instead, this is going to be a function of a variable s. So we would say that the lowercase f of t is the function in the t domain, because we've got t variables. And after taking the Laplace transform, the capital F of s is the corresponding function in the s domain. And this is a bijection between these sets of functions, meaning it has an inverse. We're not going to prove that this is a bijection because that would kind of take us down a rabbit hole that's not very productive. But we also have an inverse Laplace transform. And the inverse Laplace transform takes the corresponding capital F function in the s domain and converts it back into the lowercase f of t function in the t domain. So for the inverse, we use the notation with a script L and a -1 to indicate that it's an inverse function. And then for the Laplace transform, we use script L notation. And we always use like these curly pointy brackets for Laplace transform. I don't know why, but that's just kind of the standard, instead of just using parentheses. No idea why we don't use parentheses, but I'm just doing what everybody else is doing.
Maybe they were Laplace's favorite.
Yeah, he's a fancy boy. Yeah. So the question is, why bother taking Laplace transforms? If you go ahead and do the Laplace transform of an entire ODE, and you convert it from the t domain or the time domain to the s domain, it's going to convert your differential equation into just a plain old algebraic equation with no derivatives. So you can solve an algebraic equation. We know how to do that, ever since 11th grade or whenever you learned algebra. And after we solve the algebraic equation, we can use an inverse Laplace transform to take our solution back from the s domain back to the time domain where it matters. And sometimes this is easier than doing variation of parameters. So if your function lowercase f is continuous on some, well, it's specifically continuous on the interval where t is all non-negative real numbers, and there exists some real constants, we'll call them lowercase k and lowercase a, such that the absolute value of your function is less than k times e to the at, for all values t greater than or equal to 0, then the Laplace transform of this function exists when s is greater than a. So the little asterisk says this condition that I'm outlining in this theorem is sufficient. So if you know that your function behaves like this, in other words, your function grows more slowly than some exponential function, then you're good. You've got a Laplace transform. It exists. But if we were being, strict mathematicians, this is not a strictly necessary criterion, right? There's some functions out there that are kind of, pathological and a little bit difficult to define. But there are some functions out there that don't meet this criterion but still have Laplace transforms. I say that because you find people, like especially on the internet, who are very particular and legalistic about mathematics, right? And they'll like point out everything you say that's wrong. And so, just the small print here is that this is not actually necessary, but in our course we're going to treat this as necessary because the functions that, whatever, it's just not super important to dive into the details in this class. So exercise 3 says determine which of the following functions has a Laplace transform. What about the power function t raised to the power 999? That grows pretty quickly, right? Does that have a Laplace transform?
Probably not. I don't know.
Yes.
Connor, you got to break the tie.
I think so too.
Yeah. So even though t to the power 999 grows pretty fast, it still grows more slowly than some exponential function. Especially because I'm allowed to multiply this exponential function by any constant, right? So I can have it start off relatively large if I want to, and then just exponential functions in general grow pretty quickly, right? They grow fast. Faster than power functions. And when I say faster than power functions, what I'm talking about is like that calculus 2 sense of the word, where you take the limit as t approaches infinity of like t to the 999 power divided by k e to the at. And after you apply L'Hopital's rule 999 times, you find that this limit is 0 because the exponential function grows faster than the power function. And so that's kind of the sense in which we're talking about how quickly a function grows. We care more about the end behavior than we care about any point before the end behavior. So what about this function, 1 over t? Does this function have a Laplace transform?
I would say yes. No.
So 1 over t doesn't grow, it actually shrinks. So it's definitely going to grow more slowly than that exponential function. But why did you say no?
Because t can equal 0.
Right, yeah. We need my function to be continuous on the interval t greater than or equal to 0. But if t is equal to 0, this function is not continuous there, right? We've got a discontinuity at t equals 0. So the first one is a yes, the second one's a no. What about cosine of t? Does that have a Laplace transform? Yeah, it's continuous and it doesn't grow, just kind of oscillates. What about secant of t? Does that have a Laplace transform? No. No, specifically because it's not continuous everywhere. Secant has a bunch of poles, or a bunch of vertical asymptotes at every integer value times pi plus pi halves, or something like that. And then what about this function 1 over t squared plus 1? Does that have a Laplace transform? Yeah. So in these examples that I gave, t to the power 999, that Laplace transform is going to be pretty easy for us to find later. Cosine of t, that Laplace transform will be pretty easy for us to find later. I think this one is actually difficult. And so in our class, we're not actually going to find this Laplace transform, and there's a lot of them like this that are just so difficult we're not going to touch them. Theoretically, they exist, but it's kind of like the function antiderivative of sine x divided by x, right? Theoretically, it exists as it's a nice analytic function, but it's non-elementary, and so we don't really normally talk about that a lot outside of like power series. And so this is kind of the case with Laplace transforms. Even if they exist, they're not always easy to find. Okay, moving on. I mentioned briefly that when we are solving a second order linear ODE, we choose between variation parameters and Laplace transforms, because these are two methods that could solve the same set of problems, right? Variations of parameters can handle functions that grow quickly or have singularities in finite time. Like, what if your ODE looks like this? Tangent t has some singularities, some vertical asymptotes, if you want to call them that. And so Laplace transforms can't handle that. You can't take a Laplace transform of tangent. But you could do variation of parameters. And I think we have done that in a previous lecture. So that's a score for variation of parameters. Variation of parameters can handle functions like arctangent of t. And arctangent does have a Laplace transform because it doesn't grow necessarily. It just kind of approaches pi over 2. But even though it has a Laplace transform, it's just really, really difficult to find that Laplace transform to the point where we don't want to deal with it. And so that's another score for variation of parameters. Variation of parameters can handle Cauchy-Euler equations. Laplace transforms can't. It turns out if you take a Laplace transform of the terms on the left side of a Cauchy-Euler equation, you can do the Laplace transform, but you end up with a differential equation in the S domain, right? And so it ruins the magic of it. Really, the magic of Laplace transforms is that your S domain equation is just plain algebra. So if you take a differential equation from the T domain and convert it to a differential equation in the S domain, you haven't actually made your problem any easier. So that's another win for variation of parameters. What is Laplace transforms good at for, you know? Discontinuous functions it handles pretty well. So like a step function is a function that would look like this, where it's like constant on one side and constant on another side, but then there's some kind of step discontinuity. Turns out Laplace transforms do really well when your non-homogeneous term is a discontinuous function, like a step function. And we'll talk about an impulse function later, but an impulse function is one where like it's 0 everywhere except for one particular value in time. And then during that instant, it applies an impulse to your system. The way you might think about an impulse is like a collision between two objects, right? Like if two balls on the pool table smash into each other, you wouldn't say that they've like collided for a significant amount of time, right? Like they don't collide with each other and share kinetic energy with each other for like a second and then bounce away. It's like instantaneous. That's an impulse. So that's a win for Laplace transforms. Not to say you can't do that with variation of parameters, but you got to do a lot of breaking and stitching things together. That's what I mean by Frankenstein is, right? Like you've got to calculate a solution with one ODE, and then you stop it, and then you take those as the initial conditions for another ODE with a different non-homogeneous term, and it's like a lot of effort. It's a lot worse. So that's a win for Laplace transforms. And then sometimes students just tell me that they like Laplace transforms. They think Laplace transforms is super easy, super fast, and they hate variation of parameters. So that's another win for Laplace.
Students just say it's easier, so
Yeah,
that's a win.
that's a win. So today's goal is to take Laplace transforms of the everyday functions that we come across and develop an arsenal of Laplace transforms just so that they're kind of ready to use. The way that you might try to derive or prove a bunch of derivatives or antiderivatives so that you can just memorize them and use them later. Same idea. We're going to just derive or prove a bunch of Laplace transforms so that later on we have a bunch of tools to work with. So if I want the Laplace transform of a constant number k, this is the integral from 0 to infinity of e to the negative st times k dt. By definition, and if you haven't memorized the definition yet, shame on you. I'll go ahead and write down the definition. Okay, so what do? I say, well, you learned a long time ago in like calculus 1 or calculus 2 that integrals have the homogeneity property, where if I've got a constant multiple like k on the inside, I can just pull the k out. And what's the antiderivative of e to the negative st? The antiderivative with respect to t, so we're going to divide by negative s, and then we keep e to the negative st, and then we evaluate this at our upper bound and our lower bound. Remember when we do improper integrals that evaluating at t equals infinity means taking the limit of this expression as t approaches infinity. And what's the limit of e to the negative st as t approaches infinity? Assume s is greater than 0.
So then it would be 0.
Yeah. So if s is positive and t is approaching infinity, also positive, and you've got that minus sign, then the e to the negative big real number is approaching 0. And then we subtract what we get if I plug in t equals 0. What do I get if I plug in t equals 0? That's e to the power 0. What's e to the power 0? 1. So in the end, we find that the Laplace transform of k is k divided by s. And by the way, as we do these proofs, as we figure out Laplace transforms, we're going to have inequalities like this that say like s is greater than 0 or s is greater than something else, maybe that would be useful in like more in-depth math classes, but this is kind of just an introduction to differential equations. We're not going to talk about every single thing that has to do with Laplace transforms. And for our purposes, this part really doesn't matter, right? It's a necessary assumption to do this proof, but in practice, you're going to find that when we solve ordinary differential equations, it really doesn't matter what the S domain is. So don't worry too much about the s greater than 0 stuff. Okay, find the following Laplace transform. So the Laplace transform of e to the at will be the integral from 0 to infinity of e to the negative st times e to the at dt, by definition. Well, so then, how do I combine these two exponential functions?
You can add the exponents together, right?
Yep. So I could write e to the power something times t. What goes in the parentheses?
Negative SA plus A.
Yeah, or I could say a minus s. And then taking the antiderivative means we divide by a minus s. And then we have e to the power a minus s t. And we're evaluating this at my upper bound and lower bound. And for this problem, we're going to assume that s is greater than a. We have to make this assumption so that way a minus s will be a negative number. And that way when we take the limit as t approaches infinity, this doesn't diverge to infinity, right? If we don't make this assumption, then this expression would diverge to infinity in this limit, and we don't have a Laplace transform. So we have to make this assumption for the proof, but like I said, after the proof, this isn't going to matter anymore. So just roll with it. What's the limit as t approaches infinity of this expression? 0. And then what do I get if I plug in t equals 0? So then the Laplace transform of e to the at is 1 over s minus a. Let's do sine. So this will be the integral from 0 to plus infinity of e to the negative st sine of at dt. This is going to require integration by parts.
Yeah.
So what do I choose for u?
E to the negative st.
Yeah, and dv can be sine of at dt. So I'm taking antiderivative of sine, like negative cosine divided by a, right? So minus 1 over a cosine at, and then minus 1 over a squared sine of at. And I'm taking derivatives of e to the negative st. So that would be negative s e to the negative st and positive s squared e to the negative st. Don't forget the plus minus plus. And then when we do the tabular integration by parts stuff, we add up the terms, or multiply, I should say, multiply these factors and then add up the terms according to these groupings. And we're going to stop here because it's going to make a cycle. So after integration by parts, we find that this integral is negative 1 over a e to the negative st cosine of at. 3 negatives make a negative, so we get minus s over a squared e to the negative st sine of at plus, oh, sorry, there's a minus sign, that should be a negative, minus s squared over a squared times the antiderivative of e to the negative st sine of at. And this is, right, this is the same thing. This is still that Laplace transform. So let me write it down again. Laplace transform of sine at is equal to, what happens to this term if I allow t to approach infinity in my upper bound? It goes to 0. And then what happens when I plug in t is equal to 0? That's a 1. What's cosine of 0?
0.
1. So it's negative 1 over a times 1 times 1 at the lower bound when t is equal to 0. So for the first term, I get 0 minus negative 1 over a times 1 times 1. For the second term, the one with the sign factor, when t approaches infinity, e to the negative st approaches 0 if we assume s is greater than 0. Okay, and then if that factor is 0, everything's 0. And then what if I make t equal to 0? That's 1. What's sine of 0? 0. So for that second term, it's just 0 minus 0 when I plug in the bounds of my integral. And then I subtract s squared over a squared times the Laplace transform of sine of at, because you recognize that. So how do you rearrange this? You would, I'm just going to call this L because I'm lazy and I like shorthand. I would add this to both sides, so I'd have L plus s squared over a squared times L equals, 2 negatives make a positive, so that's positive 1 over a. And then this factor out in L is 1 plus s squared over a squared. Divide both sides by 1 plus s squared over a squared. I'm going to distribute that a. And then multiply the top and bottom by a. And we get this. This is the Laplace transform we're looking for. This is the Laplace transform of sine of a times t. In this case, maybe I should have said this more clearly, but the lowercase a is just a constant, right? That could be a number like 4. So if we have sine of 4t, in the s domain, the Laplace transform is 4 divided by s squared plus 16. And again, one of the assumptions we used in this proof was that s was greater than 0. But again, don't worry too much about that because it doesn't matter in the end. Not for us anyways. Find the following Laplace transform. There's going to be a lot of these today. What this is asking is, what happens if you have a constant multiple times a function? Right, and this would be the integral from 0 to infinity of e to the negative st times that k constant times my function dt. And because of that integral homogeneity we talked about earlier, what you find is this is the same thing as if you just take the k outside of the Laplace transform. And by the way, our standard notation is that the Laplace transform is going to be the capital letter of whatever function we're working with. So capital F of s is going to be the Laplace transform of lowercase f of t. And so in this case, you could say that the Laplace transform of k times f of t is k times capital F of s. So it works just like derivatives and just like antiderivatives and just like integrals. It's a operator with homogeneity. All right, find the following Laplace transform. This time we want the transform of f of t plus g of t, where f and g are two separate functions of time. And so this is going to be e to the power negative st times f of t plus g of t dt. But notice, I can distribute the e to the negative st, right, distributive property. I can distribute that to both f of t and g of t. And then because integrals have the additivity property, I can break apart this integral where that plus sign ends up. So this is the same using integral additivity and the multiplication distributive property as saying the integral from 0 to infinity of e to the negative st f of t dt plus 0 to infinity of e to the negative st g of t dt. And for that reason, this is just capital F of S plus capital G of S. And that means we say Laplace transforms have the additivity property as well, which means that Laplace transforms are linear operators because they have homogeneity and additivity. That's good. There's no fancy addition rules we have to learn. What if I have a Laplace transform of f of a constant c times t? So c is just a real number constant. Then this is the integral from 0 to infinity of e to the power negative st times f of ct dt. And this time we're going to have to use a u substitution. We're going to say u is equal to ct, and in fact, yeah, we can call it u. That's fine. I'm trying to be careful not to reuse symbols too many times, but I think it's okay in this case. That means if I were to ever see a t, t would be u divided by c, and I can replace the dt with just du. Because the derivative of u with respect to t is just, oh no, I can't, sorry. I would have to replace my dt with 1 over c du. Okay, now we're ready to do our substitution. And so we write the integral from 0 to infinity of e to the power negative s over c times u f of u du, and don't forget the 1 over c. That's just a constant, so I can take that outside. So this is, in purple, the formula for the Laplace transform, except what's different about it? The part that's different is instead of having an s here, I have s divided by c. And the other difference is just cosmetic, right? The other difference is I replace the t's with u's. But it doesn't matter what symbol we use, it's the same idea mathematically. Really, the difference here is that we're replacing the s with s over c. So this is the Laplace transform of my f function, but instead of capital F of s, we have to write capital F of s divided by c. So this is the result we're trying to find this time. So if you're taking a Laplace transform of a function and in the argument you're multiplying by a constant, then in the Laplace transform, you divide the argument by c and you divide the whole capital F function by c. I'm trying to show you enough of these examples so that you feel comfortable doing these at home when you do your homework. And whenever we do a test, I'm going to ask you to reproduce some of these Laplace transforms from the definition of Laplace transform, right? Just like I sometimes ask my Calculus 1 students to prove a derivative, even if they have it memorized. And I sometimes ask my Calculus 2 students to, work out an antiderivative, even if they have it memorized. Same kind of idea. Probably put a few of these questions on the next test. Find the following Laplace transform. So here we go. We got t to the n power. And I think this one's going to be kind of a doozy. You would think that this one would be straightforward because, the derivative power rule is very straightforward. The antiderivative power rule is not so bad. But you'll see what the trick is here in a minute for a Laplace transform. This is going to require integration by parts. So in integration by parts, we have this formula, right? And here we choose the polynomial to be my u, the t to the n. And that means du is going to be n t to the n minus 1. V is going to be e to the negative st. Sorry, dv is e to the negative st dt. And then v will be antiderivative of e to the negative st, which is negative 1 over s e to the negative st. So now we can write that this is u times v, which is negative 1 over s, t to the n, e to the negative st, minus the antiderivative of v du. So two negatives make a positive. And between v and du, the constants are n divided by s. E to the negative st, t to the power n minus 1, dt. Okay, in the first term, where I've got negative 1 over s, t to the n, e to the negative st, what happens if I let t approach infinity? Yes. Assuming that s is greater than 0, then as t approaches infinity, the exponential term races to 0 faster than the polynomial term can grow. And so everything goes to 0 in the upper bound limit. And then we subtract negative 1 over s times 0 to the power n, right? So that goes to 0. Plus n divided by s times this. And when I evaluate this, I'm going to have lower bound 0 and upper bound infinity. So what is this? This is the Laplace transform of
The derivative ut. No, I'm just kidding. N minus 1.
yeah, this is the Laplace transform of t to the n minus 1. whenever I have the right lower bound and upper bound here. So the Laplace transform of t to the n power is equal to 0 minus 0 plus n divided by s times the Laplace transform of t to the power n minus 1. And this is a kind of recurrence relation. I'm going to write it again without the 0 minus 0 part. Because then I think this should be equal to n divided by s times n minus 1 divided by s times the Laplace transform of t to the power n minus 2. Right, there's nothing special about the number n, so we could do the same thing with the number n minus 1. And there's nothing special about the number n minus 2. So we can do it again and again and again. And we'll reach a point where we have n divided by s times n minus 1 over s times n minus 2 over s times n minus 3 over s, and so on and so forth, until we get down to 2 divided by s times the Laplace transform of what? Yeah, t, which is the same thing as t to the power 1, right? Because the power of t is always going to be 1 less than the previous numerator. And so instead of 2, it'll be 1. And then applying this rule again, this is going to be times 1 over s times the Laplace transform of what? T to the 0. So that 0 is 1 less than the previous numerator. Okay, so now realize t to the 0 power is just 1. So here we're thinking about the Laplace transform of 1. And we've already found this, so I'm not going to make you find it again. The Laplace transform of just a constant, like the Laplace transform of 1, is 1 divided by s. So let's go sneak that back in. And what I'm going to try to convince you of is the Laplace transform of t to the n power is n factorial divided by s raised to the power n plus 1. We get n factorial because that's n times n minus 1 times n minus 2 all the way down to times 3 times 2 times 1. How many copies of s do we have? Well, we've got s kind of numbered for us according to the numerator. There's 1, 2, 3, and so on, n minus 1, n copies of s, but times an extra copy of s in the denominator. So there's really n plus 1 copies of s in the denominator. And so this is a nice power rule for Laplace transforms, because now no matter what the power of t is, you can write down what the Laplace transform of it will be. So that's a doozy. Like I said, we had to start off using integration by parts to get the first rule. And then you've got to be able to recognize when you see the Laplace transform of n minus 1, write down this recurrence relation, and then think about what pattern that recurrence relation is going to generate, and so on and so forth. But it's doable. Find the following Laplace transform. Clearly show every step of your work. So you got the Laplace transform of e to the power ct, where c is just a real number constant, times f of t, where f is any function. And this is going to be the integral from 0 to infinity of e to the negative st times e to the ct times f of t dt. So you pointed out before how I can combine two exponents and write e to the power c minus s times t, f of t dt. And this is the Laplace transform formula for the function f of t, but the only difference is that instead of having an s, we just replaced the s with c minus s. So in our Laplace transform, this is going to be capital F of c minus s, where capital F would normally be the Laplace transform of lowercase f. But if I'm also multiplying the function lowercase f by e to the ct, the way it changes the Laplace transform is you replace all of the s's with c minus s's. Sorry, I read it backwards. This is such an easy mistake to make, right? But that wouldn't be the same as replacing s with c minus s. Because in the Laplace transform formula, s should be negative. There should be a negative s that appears in the formula, is what I'm trying to say. And so this is really e to the power negative s minus c times t times f of t dt. And that would mean replacing s here where it shows up in the original formula with s minus c. There we go. So that's kind of weird because multiplying a function in the t domain by e to the ct just represents a domain translation in the s domain, where you just shift your capital F function over to the right by c units. All right. Find the following Laplace transform. I want the Laplace transform of t to the n e to the at. But you know, I'm going to rewrite this a little differently and write it as e to the at times t to the n. And as I do this, I'm going to recall two things. What was the Laplace transform of just t to the n?
In factorial over s n plus 1.
Nice, very good. In factorial divided by s to the power n plus 1. And what did we just now find was the Laplace transform of e to the ct times f of t? Very good. So now, if I see e to the at, where a is a constant, times t to the power n, can we go ahead and figure this one out without having to use the definition of the Laplace transform? Is there a way to combine these two ideas to get my answer?
Would you like multiply them together? No.
So let's say lowercase f of t is t to the power n. And that means capital F of s would be n factorial divided by s to the power n plus 1. Because remember, capital F is just the Laplace transform of lowercase f. So going back to the green, what is the green Laplace transform?
Would you replace the s with s minus a?
So I'm going to write n factorial divided by s minus a raised to the power n plus 1. Because what the previous rule taught us was multiplying by e to the ct just means you shift the domain of your capital F function by subtracting c from the argument. So we have my capital F function. All I have to do is subtract c from the argument. So I'm going to replace the s with s minus c, although this time it's an a instead of a c. Doesn't matter. It's still just a real number constant. So we write s minus a. Does that make sense? All right, next one. We've done a lot of different functions that you might see appear as like the non-homogeneous term in an ODE, like functions like t to the n and e to the t and sine and cosine and stuff. Now, what we talked about is like the real magic of Laplace transforms is we can solve ODEs. So we have to be able to take Laplace transforms of the derivative of a function. So the Laplace transform of f prime of t is going to be the integral from 0 to plus infinity of e to the negative st times f prime of t. And the way we continue is by integration by parts. When I choose my integration by parts stuff, I'm going to let dv be f prime of t dt, because I know I'm about to take the antiderivative, and if I take the antiderivative of my derivative, I'll get f of t back. And you can even see in the integration by parts formula how that's a good thing, right? If I can eliminate all the instances of f prime of t, I won't have any more derivatives to worry about. That means u has to be e to the negative st, and that means du is going to be negative s e to the negative st, right? dt. So let's figure out what that says after applying integration by parts. U times v is going to be e to the negative st f of t minus v du, two negatives make a positive, and I get the antiderivative of f of t times s e to the negative st. What happens if we assume s is greater than 0 and we let t approach infinity for the first term here? That term goes to 0. And then what happens if I plug in t equals 0? Then I would get e to the power 0, which is 1, times f of 0. And then this is going to be s times the integral from 0 to infinity of e to the negative st f of t dt. So we can write that the Laplace transform of f prime of t is equal to s times capital F of s minus lowercase f of 0. In the context of an ODE where we have like ay double prime plus by prime plus cy is equal to g of t, that means taking the Laplace transform of everything is going to be c times the Laplace transform of y, we'll use capital Y since it's a Laplace transform, equals the Laplace transform of that capital G function, which will be a function of s and not t. And then we'll have b stick around because it's, Laplace transforms have that homogeneity property. And then instead of y prime, we can put in s times y minus the initial value of y 0. Because this is the function, lowercase f, lowercase y, evaluated at time t is equal to 0. So that'll be like my initial value. And then we're about to figure out what happens with this term. We need to figure out the Laplace transform of the second derivative. That'll be important too. But this is just, the context of how important is this Laplace transform. Well, this is how we get rid of the derivatives out of our ODE. We make this into just an algebraic equation where we can solve this equation for a capital Y and then do the inverse Laplace transform. Okay, second derivative time. By the way, we already know that the Laplace transform of the first derivative is s capital F of s minus f of 0. So now, when I want the Laplace transform of the second derivative, this is just the derivative of the derivative. And so I can use this rule to write s times the Laplace transform of f prime minus f prime of 0. And that would be s times capital F of s minus f of 0 minus f prime of 0, which is s squared capital F of s minus s f of 0 minus f prime of 0. And that's how you take the Laplace transform of the second derivative of your function. And like I said, that's going to appear in our second order ODEs. So whenever you see ay double prime plus by prime plus something, 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 you're going to write a times s squared y, that's a capital Y for the capital F, minus s times the initial value of y minus m0, because that's the initial value of your derivative of your function. And so doing this makes it so that the initial value problem is baked into solving your ODE. In other words, you can't solve an ODE with Laplace transforms without also solving the initial value problem. You kind of get it for free. Maybe that's one of the perks. So this is how you convert this ODE from the T domain into this algebraic equation in the S domain. And notice it's just pure algebra. There's no derivatives happening in the S domain. You just have to rearrange that orange equation for capital Y, and then having solved for capital Y, you just use inverse Laplace transforms to get back to your solution in the T domain.